Alright, this video is on solutions. In this video we'll be identifying solvent and solutes as well as defining solutes and solvents. We're going to identify what a crystal lattice is and how it's organized. Then we'll talk about why dissolution or dissolving occurs. And then lastly, ionic compounds, and in that process we'll talk about the formula, like how to write out the formula, how to get the ions from the formula, and how to get the name or the nomenclature of the compounds. At any point, if I give you one, you should be able to give me the other two. If I give you ions, you should be able to give me formula and name. And then if I give you the name, you should be able to give me the ions and the formula. All right, so let's go ahead and start off with identifying solvents and solutes, and start off with the definition. Okay, so a solute is a substance that is being dissolved. In this case, usually we'll be dealing with salts, and sometimes we'll talk about like sugar being dissolved or alcohol being dissolved in water. But for this, the purposes of this lecture, we're mainly going to be referring to salt, or when I say salt, that's another word for ionic compound. The solvent is the substance that's dissolving the solute. So in many cases, water. Water is what we call a universal solvent, meaning it can dissolve a wide range of different types of compounds. And then other solvents include ethanol or propanol. Any type of alcohol can also dissolve substance. It can also be a solvent. Now, when it comes to the solvent, in this case mainly referring to water, if I was to draw a water molecule, okay, two hydrogen atoms and an oxygen atom, okay, I'm putting in those 4 electrons there. Those are unshared pairs of electrons, and they're going to play a part into assigning what we call the slight charges, or the dipoles of this this slightly charged particle. Even though we look at H2O and we look at it being neutral, in fact there are slight charges that are canceling each other out. But those slight charges are very important when it comes to water's ability to be a solvent. So just a little refresher from biology. If you remember that this right here, okay, and this right here, those are both covalent bonds. And within each covalent bond, okay, there are 2 electrons. One electron is from right over here, 2 electrons, and 2 electrons here. One electron is being from oxygen, and the other one is being from hydrogen. Okay, and if we remember that most atoms like to have 8 electrons in order to be happy. Well, hydrogen is one of those cases where it can take its electron and the oxygen's electron and share it between this bond and have its 2 electrons and be happy. And same thing with the other hydrogen. So both hydrogens are happy because they have 2 electrons. Oxygen is happy when it has 8. So it has these 2 electrons in one bond on the left, and it has the other 2 electrons in the bonds on the right. But it also has these 2 unshared pairs of electrons. Okay, so here's one unshared pair here. Here's one unshared pair here. So one on the left and one on the right. So altogether, that makes water neutral because everybody has their happy electrons, and everybody has the right amount of electrons, and there's no extra electrons or too few electrons, so there's no charge there. But if you take a look at any point in this molecule, the chances are that most of the electrons are going to be here around oxygen, and most of the electrons are going to be away from the hydrogens. So if we were to take a snapshot at any one point, you would probably see that a majority of the electrons are on the oxygen. And if you remember, since electrons are negatively charged, we can say even at that snap moment, at that very, that one moment in time, it looks like oxygen kind of has a negative charge because it has all the electrons. And then the hydrogens in relation to that would have no electrons, which means it looked slightly positive. So what we're going to do is we actually assign a slight, which is delta, negative charge to the oxygen, and slight positive charges to the oxygen, or to the hydrogens. So again, we're neutral. There's no, see, look, there's no charge here. Nothing there. So, I mean, there is no charge. But if you look at the actual molecule, you're noticing that at any one point there could be a positive charge on the hydrogens and a negative charge and the oxygen. And this idea of having slight charges is called polarity. Okay, so that's why when we say water is a polar molecule, that just means it has these slight and positive and negative charges. Now, the next part of this video is on the crystal lattice. So, if I was to take, say, sodium chloride, okay, sodium chloride, in fact, just for this, we'll do that. Okay, so sodiums are red and chlorines are green. So I'm going to have my chlorine right here, and then I'm going to have a sodium right here. And what's happening is this is really sodium plus and chloride minus. Okay, so these are charged particles. It's just there is an attraction between the two of them. That's why we normally see them written together as one. But in truth, there are actually two different ions, okay, or charged particles that have an attraction to each other. But as it turns out, surrounding every chlorine in every direction, okay, there's 6, there's 4 here, and then there's 1 going into the board, and there's 1 coming out of the board. Okay, so I mean, there's also 1 back behind, okay, behind it, and there's actually another one that's actually coming out towards you. Okay, so there's that chloride is surrounded, which is all positive, 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 positive. Okay, is surrounded by. So this negative chloride is surrounded by 6 sodium ions, and then if you think about it, each one of these sodium ions is also surrounded by chlorides. And what's happening is they're just repeating over and over and over and over and over. Okay, and this 3-dimensional structure, so you gotta imagine this is coming out of your computer and it's going into your computer. You have a 3-dimensional crystal, and that's why salts occur as crystals. And what they are is they're nothing more than just alternating charges of the ion, or alternating ions particles. So you'd have, a chlorine here, and then you'd have a sodium right after it, and then another chlorine over here, but it's also going out of your screen and going into your screen. So it's a 3-dimensional object. Now looking here, I have a, let's go ahead and just say, okay, so now, we know that we know what the lattice looks like. Okay, so let's go ahead and say, here's my chlorine, or sorry, sodium. My sodium here, and then my chlorine here. Now, that's negative, this is positive. So, mainly, the reason why this substance dissolves is because there is an attraction right here between the sodium and the chlorine. But the question is, how strong is that attraction? Well, as it turns out, if I have, remember, water molecules up, I got them up here to show you, remember, to remind you it's polar. If I had water oriented like this, that means that the slight positive charge is right there. Okay? And over here, I have the water molecule oriented like this, with the slight negative charges there. So the question is this attraction stronger than this attraction here, or this attraction here? If the answer is yes, this attraction right here, the sodium and chlorine attraction, is stronger than the water's attraction toward the ions, then that substance will not dissolve. But in the case of sodium chloride, this attraction is actually weaker than this one and this one, which means the water is going to pull the chloride away from the sodium, and the sodium is going to pull the chloride away from the water. And instead of having chlorides surround the sodium, it's going to have a whole bunch of oxygens surrounding the sodium. Right? And then same thing with the chlorine. It'll be hydrogens, hydrogens. Okay, and obviously there's thousands of water molecules that are surrounding it. Okay, each individual ion. But the whole point is, I know it looks like a mess if you just stand back and look at it for a second, but bottom line is, if the attraction between the water and the ions is stronger than the attraction between the ions themselves, that substance is soluble. Okay? If the an ion's attraction is stronger than the water's pull to separate it, then you would say it was insoluble. Okay? So in the next video, I'll talk about the ionic compounds, so you can complete the ionization worksheet.